Welcome to Physics Background, Chapter 1. This will be a review of SI units, order of magnitude, conversions, and significant figures in scientific notation, which go hand in hand. To start, I want you to take a look at the white bar on your screen, and I'm going to pop a couple of images into it. Start by just telling me what you think you see. A couple things you could have written. You could have said, I see 5 pieces of fruit. You could have said, I see 3 apples and 2 oranges. Let's stick with that way of thinking about it for just a second. So, if we have 3 apples and 2 oranges, the question becomes, can we add these together? Can we, in fact, add apples and oranges? Well, even if we take oranges and we slide them over, and we put them all in one big group, just like you did in kindergarten when you're adding things together, you still have 3 apples and 2 oranges. In order to truly add them together, there has to be some common thing that you convert them into. In the cases of apples and oranges, we might say fruit. So, in this case, we need to find a way to convert both apples and oranges to fruit. If we consider each apple as one piece of fruit and each orange as one piece of fruit, we end up with conversion factors, which we'll use later when we do conversions. In this case, 1 apple is 1 piece of fruit and 1 orange is 1 piece of fruit. Which means, if I count all of my pieces of fruit, I have 5 pieces of fruit, and we've successfully added apples and oranges. But that's easy fruit. Let's complicate things. Instead of oranges, let's look at grapes. In this case now, we want to add 3 apples to 2 bunches of grapes. But the problem we have here is that our bunches of grapes are made up of individual pieces of fruit. Each little grape here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 individual grapes in each bunch of grapes. So we know that every bunch of grapes has 10 grapes in this picture. And we know that 1 grape is equal to 1 piece of fruit. So in this case, if we look at the amount of fruit just in the grape side of things, for each bunch of grapes, we need to consider that as 10. So in reality, we don't have 2 bunches of grapes, we have 20 pieces of fruit. We take those 20 pieces of fruit, we add them to the 3 pieces of fruit represented by our apples, and now we have a new number of 23 total pieces of fruit. We've had to convert our grapes into pieces of fruit. The units we've been using to sort of play with this conversion has been apples, oranges, grapes, and pieces of fruit. Let's take a look at the units that we're actually going to look at this year when we need to go through things. They're called the SI units. Not feet, yards, but actual useful units, and they're useful because they're base 10 units. And in the SI system, we have what are referred to as base units: time, length, mass, temperature, amount of substance, electric current, and luminous intensity or brightness. All other units come from these units. In your head, you're probably thinking of 100 other different things that we may use, but we start from here. Take a minute, pause the video, and see if you can come up with the actual unit for each of these. Let's do the first one together. Time is measured in seconds. So even though we have minutes and hours and all these other things, our base unit that we're going to look at in physics for time is seconds. Alright, pause me here, take a minute, see if you can do length, mass, temperature, amount of substance, electric current, and luminous intensity. Welcome back. Let's see how you did. Length, our base unit is meters. Mass is kilograms. Temperature If you had said Celsius, I wouldn't feel bad because it's what we use a lot of the time. But the actual base unit is degrees Kelvin. Mole is our amount of substance. I know, chemistry flashback. It won't happen often, but it will happen once in a while. Electric current is in ampere, and luminous intensity is in candela. These base units all have a base prefix, second meters, and if you look at kilograms, it's a little different. We think of the unit as grams and then kilo as the prefix, and that's true. And in this case, a kilogram is 1,000 times bigger than a gram. So if we look at our unit prefixes, we've got the 4 that we're going to focus on during this class, which are kilo, deci, centi, and milli. I would expect at any point, if I put on a test a conversion from kilometers to meters, that you would be able to do that conversion. Or from kiloliters to liters for you to be able to do that conversion. Same thing with deci, centi, and milli. The value we'll come back to a little bit later, but that shows its power of 10. And that is going to become something that's very important as we're sort of looking at both significant figures, we're looking at measurement, and we're thinking about how we're doing our calculations. This table is on Moodle as a reference for you. There is also a similar table in the textbook. So we have other units that we haven't talked about yet. For example, volume. Volume is what's referred to as a derived unit. It has the base units are going to be put together to create a new unit. In order to get the volume of a square like this, we need to take the length times the width times the height. All of those are measured in meters. So if we think about this just in terms of the units, we have meters times meters times meters, and anything times itself 3 times is that thing cubed. So our base unit here is actually what we refer to as cubic meters. Meters to the 3rd power. We've gotten that by just multiplying all the little pieces of meters together. But when we think about volume, we often don't think about cubic meters or cubic centimeters. We often think about things like gallons and liters. Gallons is a different set of units. Liters is in the SI universe, but liters is derived from how its relationship to cubic decimeters actually. So 1 liter is equal to 1 decimeter cubed, and this is how we have derived the unit of liter. So even though it has its own letter, its own designation, it still is a derived unit. We have other derived units where we don't actually have a new letter designation for what we have, and density is an example of that. You may have seen an example like this where you put water and vegetable oil and dish soap and you let them settle, and you see how the more dense things sink, the less dense things sit on top. And you may do some calculations and say, well, if we take the mass of these objects divided by the volume, we can figure out their density and know which ones will sink and which ones will float. If you're looking at solid density, we always take grams over cubic centimeters. And you can see we have our derived volume unit built in. We have grams from our base unit as well. And that's how we measure the density of a solid. If we want to do it as a liquid, we do grams per milliliter. And now we're still using our derived units, but we don't have a new letter to represent density in terms of we just say grams per milliliter. Both types of units are derived units. All right, take a step back to our orders of magnitude and our powers of 10. Here's a more detailed diagram including each power of 10. We're going to look at a little bit of a video in class, a flash video, and we'll go over how some of this works. But the thing to remember with this is every time you jump a power of 10, which is any time you're jumping through your prefixes, you're changing the magnitude of what's happening. And something going 10 kilometers per second is much faster than something going 1, and much slower than something going 100. So keeping those zeros correct is going to be really important. There's also a 1977 video called the Powers of 10 video, which I've included a link to, which I've embedded in a file on Moodle if you want to take a look at it. All right. let's do some conversions. In every science class you've taken so far to this point, you've had to do some form of conversion. If you've taken the biology class, or sorry, if you've taken chemistry most recently, and you've been in there with Tom, he taught you a method that looked like this. Take your value, set up a multiplication problem where you're putting the meters on the bottom to make them go away, and you're keeping the kilometers on top. And if you set it up properly, you can actually do the math without any numbers to see that you're getting your unit correct. You then just have to plug in your 1 kilometer for your kilometers, your 1,000 for your meters, and you can do your math. If you took a biology class or conceptual physics with Elisa, you may have seen something that looks more like this, where it's a table setup. It's essentially the same principle, it's just about organization. We're setting up the same math problem. 1 over 100 is our conversion factor here. So in this case, we're going to take 562, we're going to divide it by 1,000, and that's going to give us the number of kilometers we need based on our meters. And again, we want to be able to do the math with the units first to make sure we have it set up correctly, especially when things get more complicated. Here are 2 more complicated equations, converting 45 meters per second into kilometers per hour. In this case, we need to set it up so that we have our kilometers showing up on top at the end and our meters canceling out, and converting our seconds, which is on the bottom of our fraction here, to having hours end up on the bottom of our fraction. So in this case, we want our seconds on top. So we end up with kilometers per hour at the end. So we know that there's in 1 kilometer, there's 1,000 meters, and we know that in 60 seconds is 1 minute, and 60 minutes is 1 hour. So we could set up that conversion and get a value. The other one that's more complicated is this: 62 centimeters squared to meters squared. And the thing that you need to remember about this is that centimeters squared is saying centimeters times centimeters. So you essentially have to do your conversion twice. And the setup would look a little something like this. Now, you'll notice I haven't put any answers into these yet. Both of these questions will be on your sort of wrap-up Moodle question sheet that you need to do at the end of this video. So go ahead and do these calculations, see what you come up with, and you're going to actually put your calculations into the Moodle review at the end of this for credit. Bad news. I will make you look at significant figures. Good news is I'm not going to take off any points for it. So significant figures are the number of reliably known numbers. So for example, here are 2 numbers with 2 significant figures, 45 and 0.062. They both have 2 numbers that are significant, and the 2 zeros in 0.062 are just showing us how big the number is and not actually important in the number of numbers. If we want to look at, here's 3 examples of 4. 45.23, we now keep 2 more decimal points from our 45. And same thing with 0.062, we're going to keep 2 more decimal points. In this case, there's zeros, but the zeros behind the 2 are important, where the zeros in front of the 6 are less important. And then 45.00 also has 4 significant figures. What about 800? The temptation is to say 1 or maybe 3, but the reality is we just don't know. Because of the way 800 is written, because we need to have those zeros there or it becomes 8, we don't know if there's 1, 2, or 3 significant figures. If it was after the decimal point, like in 45.00 above, then we would know that they are significant zeros. We'll talk more about that when we talk about scientific notation. That's why we use scientific notation, in order to clarify exactly how many significant figures we have. When you're doing multiplication and division, you always want to use the number with the least accuracy. Well, that's true in any case. In multiplication and division, that means the fewest number of significant figures. If I want to take 45 times 45.23, I can only keep 2 significant figures in whatever my answer is. Addition and subtraction is a little different, and we'll talk about that in just a second. As you're going through your equation, you may have to do multiple steps of multiplying and dividing, and there's 2 temptations that happen. One is to keep all the numbers your calculator spits at you, even if there's 47 of them. And the other one is to just keep the 2, and both strategies can cause some big problems. The easiest thing to do is to keep 1 extra significant figure, or keep the maximum number of significant figures. So if I know that 4 is the maximum number of significant figures I have in any number that I'm looking at, I'm not going to keep more than 4 significant figures when I'm going through my calculations. And only round at the very end. Let's do some examples. Here's the first one. The area of a rectangle we know is base times height, or length times width. So in this case, we're going to take 11.3 and multiply it by 6.8. We get an answer with 4 significant figures when we plug it into the calculator. But if you look at 11.3, we only have 3 significant figures there, and at 6.8, we only have 2. So what we need to do in this case is because it's multiplication, we're going to choose the fewest number of significant figures we have, which in this case is 2. So we're going to look at 76.84. 8 is 5 and above, so it means the 6 rounds up to a 7, and that gives us our insignificant figures. Our answer here is 77 centimeters cubed. In the case of addition, things are a little different. Here we've got 3.6 minus 0.57. We get 3.03, but now we can't count the number of significant figures. In the case of both of these, the answer is 2, but where the numbers are in 0.57 are very different than where they are in 3.6. So what we do in addition is we take the least accurate number, which in this case is 3.6, because it only goes down to the tenths place rather than the hundredths, which means our answer that we have has to stop at the tenths place rather than the hundredths. So we're going to take the 0 number, look at the number after it. 3 is less than 5, so we round back down to 0. So insignificant figures, our answer here is 3.0, and we don't have a unit. Take a look at these 4 values. How many significant figures? The temptation here is to say 3 for all of them. That's true for A, B, and C. But D, we don't know. Because we don't have a decimal point, and we have 2 placeholder zeros, or potentially 2 zeros that are very important, we don't know whether or not D is 3 or 4 or 5. We have a way to deal with this, and that's using scientific notation. We're going to take our numbers and write them in powers of 10. So if we have 36,900, we can write it as 3.69 times 10 to the 4th. If you take 3.69 and you multiply it times 10 to the 4th, you get 36,900. But what this shows us is it shows us that this number has 3 significant figures, and those 2 zeros are just placeholders. If we had 5 significant figures, this would be 3.6900 times 10 to the 4th. We can also go the other way. If our number is a decimal point, we multiply it times 10 to the negative of whatever that is. So in this case, it would be 2.1 times 10 to the negative third. It's like dividing by 1,000. So if we have this number, 36,900, and we want to know what it is with 4 significant figures. We change it into scientific notation, which we know is 3.69 times 10 to the fourth. But because we want 4 significant figures, we keep an extra 0, 3.690 times 10 to the fourth. When we come into, don't forget to do the Moodle follow-up. Make sure you're doing that. It'll be for credit. When we come into class, we'll go over some more, we'll work on some practice problems with scientific notation, with conversions, and we'll take a look at the powers of 10 video and just try to get our heads wrapped around how differently things can change within those powers of 10. All right. Have a good one.